Thank you for the introduction. These are my disclosures. So we're going to talk in 6 minutes about the evolution of CT. And for those of you who have been in the field for not too long, you may have gotten used to all these beautiful images. But I think it's important to remember that CT only was born basically 50 years ago. And it has seen huge evaluations and development that are quite revolutionary. Very shortly, so it started with Hounsfield and Ambrose in 1971, and already in 73 there was the first US installation. And before the end of the 70s, there were millions of CT scans already being made in the US. You see here on the left side an image of the first clinical type scanner, where each image took a couple of seconds. So you had to have a number of breath holds to even make a scan of the chest. Now the next revolution, I think, came around 1990. Okay, for those of you who are in this field, I skip electron beam CT for now, because that was even before. But calendar was basically at the basis of slip ring technology, which allowed continuous rotation of the detectors, of the X-ray. And this technology allowed whole organs to be imaged within one breath hold. You see here a single slice spiral CT, and in the next years, at the end of the 90s, early 2000s, you saw the increasing number of slices in multi-detector CT. And this resulted in shorter exam times, longer scan range, higher spatial resolution, and finally, isotropic voxels that for the first time allowed 3D images, for example, for vascular imaging. Well, there are multiple other developments, including improvement in X-ray tubes, X-ray detectors, kernels, etc., but time is not enough to go into that. Another point that I would like to address is that at the early 2000s, we saw the change from analog images to digital PACS and filmless radiology department. And around 2010, we got the introduction of iterative reconstruction techniques and now also deep learning reconstruction techniques that allow much lower image dose with higher image quality. And photon counting CT is the newest revolution that already was addressed this morning. Now, when we correlate this with the timing of the CT lung cancer screening studies, of course, the first one started with the I-ELCAP group. That was already in 1992. So that was just after the introduction of single slice spiral CT. Newer trials, including NLST and Nelson, were all started when we already had multi-slice, multi-detector CT scanners. With thanks to David for providing these images, what we need to realize that when I-ELCAP started, this was still CT scans images printed on film. So you see here 12 images printed on film on the viewing, what do you call it in English? The viewing machine. And so this is the way that these images were made and processed at the beginning. A 10 millimeter collimation reconstructed with 5 millimeter increments. And if a nodule was detected, additional high resolution images were made focused on the area of the lung nodule, as you see here on the right side. So we've made a remarkable change in the way that we do radiology since then. That, of course, was also implemented in I-ELCAP. But even in those early years, you see here the diagnostic CT scan that was made in I-ELCAP for a lung nodule. Those were already quite revolutionary images of 3D of a lung nodule, even with some thicker slices. And this one showed actually growth on a short-term repeat scan. Now, clearly, we started with 10 millimeter slices. We're now down to less than 1 millimeter slice thickness. This truly impacts nodule detection and nodule quantification. I won't go into detail. This is just one example. On the left side, 5 millimeter scan, you see kind of a hazy, maybe ground glass nodule. On the right side, it's a clear conspicuity, and it's a clear PFN. Now, I think I would like to address a couple of words to Nelson. This study really took advantage of the developments in CT of being able to get isotropic voxels. And that means that we can get a 3D volume. And that means that we do quantification of the volume of the nodule and looking at the actual volume doubling time. And we use this in the short-term repeat scan to look at the VDT so that not everyone with a suspicious nodule was directly sent to the pulmonologist, but it was based on short-term growth. And yes, this has an impact on referral rates and on outcomes. You see here just a very schematic overview of the comparison between usually manual diameter measurements and automated volumetry. So both factors play a role in the accuracy and the variability. On the left side, when you have a nodule from 80 to 100 cubic millimeter, it grows by 25% in volume, but the increase in diameter is only 0.4. And that's not something that we can recognize by just doing measurements. On the other hand, when you do have, according to the criteria, an increasing diameter of 1.5 millimeter or more, then you have a near doubling of the volume. So using volumetry, which became possible with multi-detector CT scanners and thin slice reconstructions, we are now able to have a faster detection of growth. And this is now the basis, at least in Europe, for lung cancer screening. Now, lastly, very shortly, what is the revolution in photon counting CT? This is the way that the CT is usually made so far, where each X-ray photon that comes into the detector is first translated into light, and that light can scatter or eventually end up on the light sensor. And that results in basically an averaging of all the information on energy. In contrast, in photon counting CT, each individual photon with its energy is directly measured without conversion. And here you have no scatter of light, and you have this information on energies, which allows to illuminate the noise, but also allows much smaller pixels. You see here comparison 0.5 is very common in the common state-of-the-art EID scanners, and 0.15 is what we now have in photon counting CT. And that, I think, is a revolution that will optimize the quantification of nodule measurements even more. You see on the left side of a phantom study, where also this low contrast subsolid nodule is detected better. But you also see on the right side a very low dose image with photon counting CT on the right. You see more detail. The nodule is better characterized and better quantified. What the role of photon counting CT could be in screening setting, I'll gladly discuss with you. Thank you.